Hello guys, in this video we will learn the inner workings of Word2Vec algorithm, how we learn the embedding metrics and how the numbers are obtained, as you can see in this particular table here, right? So in my part 1 of this Word2Vec video, I have given you the general idea why we may need Word2Vec and why bag of words and TF-IDF fails, right? So the general idea is words used in similar ways or have similar meanings should be given similar numbers. In other words, they should be grouped together or they should be placed nearby. Okay. The second point is the same word can be used in different contexts, right? And they can be used to infer completely different sentiments, right? So for example, in this particular two sentences, the first one says, "It feels so great to play cricket after a long time." So in this sentence, the word great expresses kind of happiness, right? But in the second sentence, it's saying, "I broke my leg today, great." So in some way, the great word in this particular sentence is expressing a kind of sadness or anger, right? Which is quite opposite to what it expressed in this particular sentence, right? So the same word is expressing two opposite emotions. So it is worth giving more than one number to the same word also. So that's the general idea, right? Now you can see in this embedding matrix here, the word great, the example that I took just now, the word great, right? So I have happiness and anger as my features here or the dimensions, right? So the great is being expressed in form of happiness. So it is getting 0.76, but the same word great is also being used to express the emotion anger, right? So it is having similar value, but the signage is negative. So if you draw this in a 2D space, if here is the happiness, anger will be somewhere here, and the great will be mapped to these two values. Okay. So this is how we try to learn the associations with the meanings for the words. Okay. Hope it is clear till now. Okay. Now, if you check king and queen, right? Is it something related to royal? Yes, correct. So king are supposed to be royal and queens are also supposed to be royal. So for the feature royal, I'll have the high value 0.93 and 0.98. Okay. And the rest values which are not associated with royal will have some less values. So cricket is not associated with royal, so it may get some very less value, 0.3 or 0.03, something like this. Okay. So when it comes to gender feature, I can get to know a general idea when I compare man and woman words, right? Man is a male, woman is a female, right? So the gender will have similar value, but the signage will be negative, right? Now if you plot man and woman in this 2D space, man will be somewhere here, woman will be somewhere here, right? If this is expressing the gender, correct? So this is how we have to learn the word vectors for each of the words in our vocabulary by deciding on the number of dimensions that we want to have, right? So in general, in reality, you will not see these feature names, okay? In Word2Vec model, you will never see these feature names. I am just writing these things to give you a brief idea how these features are used and how these numbers are obtained. Okay. So these can mean anything. For machine, it means nothing. But for our understanding, I am just writing it down. Some of the features which may be used, right? For example, great word is used to describe happiness and also to describe the anger, right? So this is how it is actually. Now, how we achieve this? How we learn this embedding matrix? So the answer is, it's a simple two-layer neural network, which is a Word2Vec model. So we'll have an input layer, we'll have a hidden layer, and we'll have the output layer. And one more thing before going into that network, the number of features or the dimensions here, I have right now written down 8 features, right? But in reality, it comes with some 100 dimensions or 300 dimensions or even 200 or 500 dimensions as we desire. The one which is trained by Google, the Google Word2Vec model, right? So this has been trained on Wiki around billion words in 300 dimensional space. Okay, so what 8 features you can see here, we will have 300 such features represented in the Word2Vec model trained by Google. Okay, so keep that in mind. So now coming to this architecture, the input layer will have so many number of neurons as many number of words we have in our corpus, or the length of the vocabulary. Okay, the output will, the number of neurons in the output layer will also be equal to the number of words in our vocabulary. Okay, now the number of neurons in hidden layer is an interesting task. So how do we decide on the number of neurons present in the hidden layer? So this is basically decided based on the number of dimensions that we want to use, right? For each word, in how many dimensional vector space we want to represent that. It depends on that part. So here in my example, I have taken only 8. So it can have 8 neurons in hidden layer. But as I told you, the Google trained Word2Vec model, it is trained for 300 dimensional vector space, right? So the hidden layer will have 300 neurons associated with it. Okay. And what activation function will this hidden layer have? All the neurons is just a linear activation function. Linear activation function. Okay. And this is not supplying any non-linearity. It is just helping us to add the numbers that is obtained from this input layer. And it is doing nothing else. Okay. So that's the overall view of our Word2Vec neural network. And this layer, input to hidden layer, will have the weight matrix. Also hidden to output layer will have another weight matrix. So W of 1 represents the weight matrix for input layer. W of 2 represents the weight matrix for output layer. Okay. Now the output layer will have so many neurons, right? This will be having the softmax activation function. Okay. And in order to update these weights to get the correct predictions, we will make use of cross entropy as our loss function to reduce the loss. By propagating backwards in the neural network and updating weights, we will try to reduce this cross entropy loss. Okay. Now there are 2 ways to train this neural network, Word2Vec neural networks. So they are CBOW. CBOW stands for continuous bag of words. Continuous bag of words, and other one is Skipgram. Okay. So for our simplicity, for our understanding, let's take, we have a sentence, I played cricket today. So how this neural network is trained? By CBOW approach. Okay, that I'm going to explain now. So what happens in CBOW approach? I will provide I and cricket as input to my neural network, and I'll ask it to predict the output, and I'll train this network till I get the correct output, that is played, which is our middle word. So what I'm doing here, I am supplying the context I and cricket and asking it to predict the target word played. So this is how we train our neural network in case of continuous bag of words approach, that is Word2Vec model. How do we train the Word2Vec model in case of Skipgram approach? So what I will do in that case, I will supply played, this word, as input and ask my neural network to predict the context surrounding it. So I want my neural network to take played word as an input to it and predict the words I and cricket which are surrounding to it as the context words in the output layer. Okay, so this is how we train our Word2Vec model with the Skipgram approach. Okay, so hope that's clear. Now you guys might have some question. While we want to learn these numbers, why we are actually predicting the words, right? What's the logic behind it? So I'll explain it in my next section. Now, the section, this is just a section heading, please ignore it. So I am just telling here how we are learning this matrix here, how we are coming to this, arriving at these numbers. Okay. So to understand that, let's again take the same sentence, I played cricket today, right? And this is the corpus. This is all we have. In our corpus, we have only one sentence, that is I played cricket today. And out of this, I will construct my vocabulary, right? So vocabulary generally will be in alphabetical order. So if I write down the vocabulary present in this sentence in alphabetical order, it will be cricket in the first position, I in the second position, played in the third position, today in the fourth position, right? Next, what I will do, I will convert each of these words into my one-hot encoding vectors. So now the size of these one-hot encodings will be equal to the size of my vocabulary. In this case, it is just 4, correct? So my one-hot encoded vectors will be of size 4. So you can see for word cricket, the first position will be 1, rest all will be 0. For the word I, which is occurring at the second position, the second position will be 1, the remaining 3 spots will be 0. For the word played, which is at third position, the third position in the vector will be 1, remaining all will be 0. For the word today, which is at fourth position, the fourth bit will be 1 and the first 3 bits will be 0 in the one-hot encoded vector. So this is our first and second step. What's the first step? We will prepare the vocabulary in alphabetical order and then we will have the one-hot encodings for that, right? Now again, considering the same sentence, I played cricket today, right? So what I will do, how I will arrive at these numbers, we will see now. Guys, please listen to it carefully. It's very interesting and it's very easy also. It looks complicated, but it's not, okay? So we have our input layer here, correct? This is our input and this is our output. This is our hidden layer, okay? So for our simplicity's sake, let's say we want to represent each word in a two-dimensional vector space, okay? Let's say we want to represent each word in two-dimensional vector space, right? So what is this two-dimensional vector space again? So it's the same thing. Like the Google trained model will give us the words with 300 dimensional vector space. So for our understanding, to understand in a simple way, I am just considering we want to express or represent each word in a two-dimensional vector space, okay? So this is what my assumption is right now. So that's why I have 2 neurons in my hidden layer, okay? Hope that's clear now. So this is how my Word2Vec model architecture looks like, as I have explained it before here, but with the only sentence in our corpus, okay? So I played cricket today. Output, again I played cricket today. So the what I told earlier, the number of neurons in input and output would be equal to the number of words we have in our vocabulary. So that's matching now. And also this hidden layer will have 2 neurons because I want to represent each word in 2-dimensional vector space, okay? Now, in case of training, while I train, I'll randomly initialize these weights to some numbers, right? So each layer of the neural network will have some weight matrix associated with it, which will help us to reduce the loss function in the end. So in this case, or in general, if we have softmax activation function as the output, right, we will make use of cross entropy as our loss function, okay? Cross entropy as our loss function. So in order to reduce this loss function, right, the total cost, we will update this weight matrix, the values, while doing back propagation, okay? So the assumption for this is, you guys already know what is back propagation is, and you know what softmax is and what cross entropy is, okay? If you do not know, that's okay. You can take my word for that. I will release separate videos for each of these: back propagation, cross entropy, softmax, and a hell lot of other activation functions, okay? So don't worry about that. Now that we have defined this architecture, what I'll do, I'll start training my neural network. So again, I can either use CBOW, continuous bag of words, or Skipgrams, okay? So let's say right now I'm inputting I and cricket as my input, okay? I'm not providing input for other words into my neural networks, and I want my neural network to predict the word play. Rest all should be 0, okay? So this will not happen at the first shot itself, right? So initially what we do, we will initialize this weight matrix. We will have one forward pass, okay? When I say we will have one forward pass, I will supply my inputs to the neural network. I will ask it to predict the output. If the output is not correct, the cross entropy loss will be high, in order to reduce that loss function, I will back propagate and update these weights in the both layers, weight at the layer 2 and weight at the layer 1. And again, I will do the forward pass until and unless my loss is reduced and I have my correct predicted output word. In this case, the input is I and cricket. I want it to predict played as my output word. So till I obtain the output word played, I will keep on updating the weights by doing back propagation at each iteration. Okay. So this is how I train my neural network. This is in case of CBOW. In case of Skipgram also, nothing changes, just the input changes, right? So in case of Skipgram, I'll input played. Okay. So let me just rub this 1 and 0. So for Skipgrams, I will be inputting played. Okay. So this will be 1 and I want it to predict I and cricket, the context surrounding the word played, right? So input will be played, output will be I and cricket, rest will be 0. So I'll again train my neural network by supplying played as input and I'll train it unless and until I get my correct output, I and cricket. Okay. So while doing this, we will have multiple epochs, right? Multiple iterations forward and backward. So I will do multiple times forward propagation and the same number of times I will also do back propagation till I get the desired output. Okay. And while I am doing all these things, I am updating this weight matrix present at the first and also the second layer. Okay. Now let's say we have trained our model either with CBOW or Skipgram and we are satisfied with the output that I am getting by supplying the words. Okay. Now in this case, once the training is completed, I will have my weight matrix separated for layer 1 and layer 2. So this is how the weights look like. For layer 1 in this particular neural network architecture, the size of the weight matrix will be 2 cross 4. Why it is 2 cross 4? Because we have 2 neurons in the hidden layer and 4 neurons in the input layer. And the weight for the weight matrix for the second layer will have the size 4 cross 2. Why? Because we have 4 neurons in the output layer and 2 neurons in the hidden layer. Okay. So we have to always look from right to left in order to determine the shape of the matrix. Okay. And this shape, the numbers depends on the number of neurons present in hidden and output and input layers. Okay. So this is our updated weight matrix. Updated weight matrix for layer 1. Right? And this updated weight matrix is nothing but our word embeddings. Okay. So how do you obtain word embeddings for each of the words? So in our vocabulary, I have 4 words, right? Cricket, I played today. Correct? So what I will do, I will take this one hot vector and I will have it multiplied with this particular weight matrix. So cricket is having this representation, 1 at the first position and remaining positions are 0. So once I multiply this, what will be the output size, guys? So any guesses? So the input, the matrix 1 is of 2 cross 4. The matrix 2 is of shape 4 cross 1, right? And the output will be 2 cross 1, right? So for the word cricket, this is the one vector for cricket, right? So for the word cricket, I will have the word embedding of shape 2 cross 1 or it's a 2-dimensional vector space, right? So like this, to get the word embeddings for I will multiply the one hot encoded vector for I with this weight matrix. Which weight matrix? The weight matrix of first layer, not the second layer. We will use weight matrix of the first layer as our embedding matrix, and whatever values we have for each of these spots, those will be similar to what we see here. 0.93 minus 0.86, 0.52, 0.03, 0.06, something like that. Okay. So this is how Word2Vec model is trained. Okay. And this is the overall architecture. So you can use either CBOW model or Skipgram model. So in what scenarios we will use CBOW or Skipgram? So generally, if we have less size corpus, if the corpus size is less, we will make use of CBOW. Okay. If we have huge corpus, we will make use of Skipgram. Okay. So this is the general idea. So hope it's clear, guys. There is another thing called as negative sampling. I will cover that part in my next video because it's related to the optimizing the working of this neural network. I'll have to explain the weights again, and then I have to explain you what do you mean by negative sampling. I'll cover that in my next video. So if you guys have any questions regarding this particular explanation, please reach out to me in comment section. I'll be more than happy to help you guys. So if you guys have not subscribed to my channel, please do subscribe and like the video and share the word across if you like this. Stay tuned guys for the next videos. Happy learning. Bye bye.